It's in there. We don't want to do it. Or like you do all the papers are, you know, like I think I put the password in. We can do it.
Yep. All right. So we'll wait
10 seconds or 20 seconds.
Hi, everyone. I'm here to talk to you about a peer mentorship opportunity going on in the Faculty of Science. So this is a good opportunity to potentially give back with some of your hard-earned wisdom and lessons to some of the students just coming into your program. Link off the board will take you here. If you join the focus group to help develop peer mentoring, you will get a free pizza lunch. So that is always a nice thing to have. Thank you.
Okay, yeah, no problem. Okay, good. And so if you're interested in this, apparently I'm going to get a poster and I will post that onto Canvas. Sorry, not Canvas, Piazza. And I assume it'll have that URL in there. Okay, so good. First, about the midterms, I've started grading. I've not finished. I will return them on Monday. I also plan to eventually post the solutions. I mean, the truth is I'm ready to do that now, but we have a couple people that still haven't written the midterm, and I don't want to give any appearance of some advantage to those students. So I will hold off for now, but the solutions will be made available shortly. Okay, good. So a week ago, we were talking about these Lengendre polynomials, and we're off on a bit of a tangent, but I think it's a useful one. And I just want to finish this off. What I plan to do today is we'll review some of the things that we already know about Lengendre polynomials. And then what I want to do is I want to say, can we come up with a bit of an algorithm to construct a set of polynomials that are all orthogonal to one another? And we'll follow that algorithm and we'll find out that what we're actually doing is generating the Lengendre polynomials. Okay, so let me remind you about what we saw already. We saw that here's the first 6 Lengendre polynomials from P0 to L equals 5, P5. And all of the ones with even L are even functions. So P0 is this straight line along the top. P2 is this green parabola. P4 is the symmetric purple one. The other thing we know is that the even numbers of L have only even powers of X in that polynomial, and the highest order or the highest power of X is given by L. So the P4 Lengendre polynomial, its highest power of X is X to the 4th. Oh, they're vacuuming the street out there. That's what we're hearing. Okay, and then the odd ones, the odd values of L have only odd powers of X. And again, like P3, its highest power of X is P cubed. The other thing we knew is that all Lengendre polynomials, when evaluated at X equals +1, equal 1. And when evaluated at -1, the odd ones equal -1 and the even ones +1. Okay, so we talked about all that. We also talked about inner products. This inner product was analogous to like dot products in linear algebra. And we used this concept that in linear algebra, if 2 vectors have a dot product that's 0, that means they're perpendicular or they're orthogonal. And so we defined this idea of orthogonal functions are functions for which this inner product, which is given by this product of the 2 functions integrated over whatever your domain is. If that's 0, then we say functions f and g are orthogonal. we kind of came to the realization that the sine functions like sine omega and sine 2 omega and sine 3 omega, sine 4 omega, those are all orthogonal functions. And what we can do is we can create any function f of x on some interval as a sum of sines of different frequencies. That's the Fourier series. And the coefficients in front of each of those sine terms is the inner product of f with sine of whatever. Okay, so we went through and we kind of went through a bit of a hand-wavy argument that said, you know what? All Legendre polynomials are orthogonal. So if I have two different values of L and L prime, where they're not equal, then this inner product will always be 0. That means I could take any function f of x on -1 to 1. And I could write it as a linear superposition of Legendre polynomials where the coefficients are the inner products or the projection of f onto each of those polynomials. And I think that's essentially where we ended off. What we're going to do today is we're going to figure out a scheme for constructing a set of orthogonal polynomials. And then we'll show that when we follow the scheme, we're actually generating Legendre polynomials. Okay, so here's a motivation in linear algebra. And we talked about this a week ago as well. I could solve problems in three-dimensional space using x hat, y hat, z hat, no problem. It's just more convenient in some situations to use a different set of orthogonal unit vectors. They could be the spherical ones or the cylindrical ones, for example. And so the question is, if we wanted to develop a set of orthogonal basis vectors or functions, what is the procedure? So we'll work out this procedure and then I'll tell you what the name is, but let's see how we could do it. So in general, how an alternative way of asking the same question is, how can we construct an orthogonal set of vectors? Okay, so what we're going to have to do is the first step is we just choose an arbitrary vector. You know, the first one doesn't have to have any specific orientation because it didn't have to be orthogonal to anything. So what we're going to do is we're going to start by supposing that A1 hat is going to be one vector in our orthogonal set. And the choice of A1 hat is arbitrary. So how can we take a second vector, B, and use it to construct something that is orthogonal to A1 hat? All right, so let's draw some pictures. Let me take as A1 hat, let's see, I want to draw this reasonably. A1 hat is arbitrary, so I'll say it's this vector A1 hat. And then let's suppose that our vector B is some other vector, something like this, B. It's clearly not perpendicular to A1 hat. Okay, so what are we gonna do? We're gonna start by considering the dot product between these two. One is consider B dot A1 hat. All right, well, we know how to calculate that. We take the length of B, we take the length of A1 hat, and we would multiply by cos theta. But if I've chosen A1 hat to be a unit vector, then the length of A1 is just equal to 1. And so what we end up with then is just the length of B times cos theta. Okay, and so I can draw that. This is going to be theta would be sitting here. And if I drop down a perpendicular, then this dashed blue line is going to be B cos theta. Okay. Now let's imagine that we took this B cos theta and we subtract it from the original vector B. Well, what would that look like? B cos theta with a negative sign is something like this, B cos theta with a negative sign in the direction of A1 hat. Is that vector? So if I take that dashed line vector on the top and add it to B, what do we get? We get a perpendicular vector like so. So this green vector is B minus B cos theta A1 hat, or it's B minus the inner product, or the, well, I'm getting ahead of myself, the dot product of B and A1 hat in the A1 hat direction. Okay, so that's the prescription for making a second vector that's orthogonal to A1 hat. And now this green vector could be a member of our orthogonal set. Okay, so let's write that down in words. 2 is next. We consider B minus B dot A1 hat in the A1 hat direction. This vector is perpendicular to A1 hat. Okay, we could check it, right? We can take the dot product of this new construction that we've come up with, and we'll take the dot product with A1 hat. If they're really perpendicular, this should be 0. Okay, well, you could probably see pretty quickly that it's going to work, because the first term is going to be B dotted with A1 hat, and then we're going to have minus B dotted with A1 hat, and then it's A1 hat dotted with A1 hat. But for unit vectors, that's just going to be a 1, and then we end up with 0. So that worked out well. Okay, now there's no guarantee that the length of this new vector is 1. So it may not be a unit vector. Okay, so let's define a 2 vector as this thing we constructed, which is perpendicular to A1 hat. And what would we do if we wanted this thing to have a length 1? How would you ensure that? Yeah, so we could normalize A2 by finding A2 hat is A2 vector divided by the length of A2 vector. So we take the dot product of A2 with itself and then take the square root of that. Okay, So now we have a set of two vectors that are perpendicular. Now we imagine, all right, I'm gonna take vector C and I want to make a third vector in our set that's orthogonal to both A1 and A2. So this will be the last example, and then we'll generalize to functions. So to construct a third orthogonal vector from C, it needs to be perpendicular to both A1 hat and A2 hat. Okay, well, let's see. We're going to say A3 is going to be our vector C minus C dot A1 hat in the A1 hat direction. This is exactly what we did for A2. I just copied that down exactly. I just replaced B with C. So this, if I stopped here, would guarantee that A3 is perpendicular to A1, but not necessarily to A2. So we would then do the same sort of procedure. You could write down these vectors and you could show that if we subtract off an exactly analogous component, then this A3 vector would be perpendicular to A1 and A2. I probably meant this to be a hat. Okay, so this A3 would be perpendicular to both A1 hat and A2 hat. And then you could generalize this. So if I wanted to make A4, I would take D and I would go minus D dot A1 hat in the A1 hat direction minus D dot A2 hat in the A2 hat direction minus D dot A3 hat direction. And you could go on and on and on and make all these orthogonal vectors. So this method has a name. This method of constructing an orthogonal set of basis vectors is called the Gram-Schmidt method. And what we're going to do is we're going to extend this method to functions, not just our usual vectors. So it can be extended to functions. And so here's the meat of what I wanted to get to. Suppose we start with the set of functions. G is equal to, it's just all the powers of x, okay, up to infinity. We know from, for example, Taylor series that I could basically write any function I want in terms of different powers of x as long as I pick the coefficients correctly. Okay, so this is certainly a basis set. They're not orthogonal, right? And you can tell they're not orthogonal because if I did 1 times x squared and integrated on -1 to 1, I'm going to get x cubed over 3, evaluated at the limits. It's going to be 1/3 minus -1/3, which is 2/3. And so, for example, these two members of the set are not orthogonal, and there's lots of others. So what we're going to do is we're going to start with this basis, apply the Gram-Schmidt method to construct an orthogonal set of polynomials. Okay, so let's use the members of G to find an orthogonal set of functions. Okay, so I guess I called that F for some reason. So our functions will be F0, F1, F2, and so on. All right. So remember in that method, the first step was you have a free choice, and we're just going to choose one to be part of our orthogonal set. So we first arbitrarily set F0 equal to 1. All right, then what are we going to do? Well, we go back to here and we say, okay, sorry, I want the A2. We take P minus the inner product of P with A. Okay. So we're going to say the next member is going to be G1, which will be X in our set G, minus the inner product of F0 with G1 in the F0 direction. I'm going to add one more thing. Notice that when we did this with our basis vectors, we made the dot product with a unit vector. And so I don't have a unit vector here. My functions aren't necessarily normalized. So I'm going to normalize them by dividing by the inner product of F1, our basis vector. So let's just see what all this looks like. I know it looks complicated, but it's not actually like that. G1 was just an X. So we have an X minus the inner product of F0, which is 1. So the inner product is going to be the integral from -1 to -1 times 1 for F0 times X for G1 dx. And then F0, we have to multiply by a 1. And then we have to divide by this inner product of F0 with itself, which is 1 times 1 times dx. Okay, so that's what that notation means. And well, maybe you could tell me what the answer is going to be. What's this integral in the numerator? X squared over 2. When you evaluate at the limits, what do you get? 0. Because you're going to get x squared at 1 minus x squared at -1, which is just 1 minus 1. And so this is a 0. So I won't bother evaluating the other integrals. We just say f1 is equal to x. Well, that's easy. So let's do the next one. F2 is going to be G2 minus the inner product of F0 with G2 times F0 divided by this normalization factor minus the inner product of F1 and G2 times F1 divided by a normalization factor. Okay, so let's see what we get this time. Let's go back and look at G2. 0, 1, 2 is x squared. Okay, so G2 is x squared minus, okay, inner product. F0 was 1. G2 is x squared minus 1 to 1. And then we have to multiply by F0, which is just 1. So if I want, I can put a 1 there.
The inner product of function of itself is always 1, right? So we're always dividing by
No, it doesn't have to be 1. If it's normalized, it will be 1. If it's not normalized, that's why in quantum mechanics you always have to divide by psi. That's the inner product of the wave function with itself. That's the normalization factor. So F0 is just 1. So then we have divide by dx, I think. And then we have minus The integral from -1 to 1, f1 is x, g2 is x squared dx. f1 is x, and then we divide by -1 to 1 of, I guess that's x squared dx, I think. All right. Let's start with the easy one. What's this interval going to evaluate to? 0. Right? We're going to get x cubed. When we integrate, we'll get x to the 4th. And then when we evaluate at the limits, those will vanish. So this is 0. That's nice. So what do we have? We have x squared minus, this is going to give us x cubed over 3, evaluated at the limits. Let's just write it out, I guess. So x cubed over 3 minus 1 to 1. This is going to give us x between -1 and 1, which is going to be x squared minus, it should be 2/3 divided by 2. I think it's 1/3, like so. And did I get that right? No, I didn't. Sorry. What does it give us? It gives us not a third. What do we get? 1/6, right? This one gives us 2/3 divided by 2. Oh, yeah, it is 1/3, isn't it? Did I get that? I think I just have it wrong in my notes. So -1/3. I hope I have it wrong in my notes. We'll find out. Okay. So what we have then so far is f0 is equal to 1. That was an arbitrary choice. f1 is equal to x, and f2 is equal to x squared minus 1/3. Now let's check our Lengendre polynomials, PL. And, well, okay, let's do it like this way. Let's say L and PL. 0 was just 1, so that's okay. 1 was just x, that's okay. Let's look at L equals 2. That one was 1/2 of 3x squared minus 1. All right. So how are these two related to one another?
One is a factor of 1 over 3, 1 factor of 1 over 3, so times 6.
We have, so let's say we wanted f2 to be, okay, let's suppose we wanted the Lth polynomial to be some coefficient, I won't use c, I think we used that already. Let's say bl times fl. Okay, so if I want p2, I would want 1/2 of 3x squared minus 1 is equal to some coefficient b2 times f2, x squared minus 1/3. Okay, let's factor out a 3 from this. So it'd be 3/2 x squared minus 1/3. And so what we end up with is that this b2 is equal to 3/2. So this construction, we've only done the first 3, but the first 3 orthogonal vectors that we get, the first 2 were exactly the Lengendre polynomials, and the third one was a scaled version. But think of unit vectors, right? X, Y hat, X hat, Y hat, Z hat. If I take X hat and I scale it, it's still orthogonal to everything else. It's still part of an orthogonal set. It's just not normalized to have a usual length. If we went and found f3, we would find that it's a scaled version of the third Lengendre polynomial. So if you find f3, that will be equal to x cubed minus 3/5 of x, and that is just 5/2 times the third Lengendre polynomial. So all of the vectors, or let's say functions, in our orthogonal set, orthogonal, let's spell that right, orthogonal set F are just scaled versions of the Lengendre polynomials. P. Okay, good.
I past three halves, usually always continue, and will that relationship stay similar, or it's like a n plus?
Yeah, I don't know. I haven't worked it out. But this factor is in some ways arbitrary. What they've chosen the Legendre polynomial scaling factor to guarantee that PL evaluated at x equals 1 is equal to 1. Right.
So the Legendre polynomials are not.
They're not orthonormal. Yeah. But that's okay. You know, the trig function sine are not an orthonormal set either. They were just chosen the coefficients to be so that the amplitude is always 1. But we didn't have to make that choice. We could have made the sine functions orthonormal, but then you would have had to remember different coefficients in front of the different frequencies. Yeah. And we don't want to remember stuff like that. Okay. And so actually my final comment is exactly what you were referring to. And it's the fact that they're not normalized. One final comment. This will actually be important for us when we solve our E&M problem in a second. A function f of x is said to be normalized. And I know you know this already. If its inner product with itself is equal to 1. So specifically, if I take two functions and I find their inner product, and so on our domain A to B, if that is satisfied, then we would say that they are normalized. And if they're part of a set of normalized orthogonal functions, that set would be orthonormal. Okay. The Legendre polynomials are not normalized. But we will need to know what their inner product with themselves are equal to. So rather, what we have is the integral from -1 to -1 of PL x and PL prime of x dx, which is just PL x inner product PL prime of x oops, it's equal to. Okay, so what it's equal to is the following. It is delta L prime times 2 over 2L plus 1. So if L and L prime are different, the delta, the Kronecker delta gives a 0. If they're the same, the Kronecker delta is 1. So another way of saying the same thing is it's 0 for L not equal to L prime. That's the orthogonality condition. And they're equal to 2 over 2L plus 1 when L is equal to L prime. And so that's our normalization factor, if you like. All right. So there's more than you wanted to know about Legendre polynomials, and it's more than is described in the textbook. All right. So how are we doing time-wise? Okay, we got a bit of time. So what I want to do is I want to get back to doing E&M now. And we're gonna do our separation of variables technique to solve Laplace's equation. But we're gonna do it in spherical coordinates with some limitations. So. Rifts. So now we're in section 3.3.2, and we're going to talk about separation of variables in spherical coordinates. All right. So you could go to the inside cover of Griffiths and you could look up the Laplace operator in spherical coordinates, and what it's going to be is 1 over r squared d by dr of r squared dv dr plus 1 over r squared sine theta d by d theta sine theta dv d theta. It's a mess, okay? Plus 1 over r squared sine squared theta d to the d phi 2, and Laplace's equation says that all of that would have to be equal to 0. All right, we're not going to solve this whole general problem. What we're going to do is we're going to assume that our potential has azimuthal symmetry. So that means no matter what the value of phi is, where you are in that xy plane, if you look around, the potential will be identical. And so there's going to be no phi dependence to the potential. So we will assume azimuthal symmetry such that V is only a function of r and theta, and any derivatives of V with respect to phi are 0. Okay, and so then if we go back up here, we're just going to kill that last term. So when we do our separation of variables, we're going to write the potential as a product of functions, one that's a function of r and one that's a function of theta. There will be no phi dependence. So our separation variables will lead us to v of r theta is some function of r times some function of theta. So this is my capital theta. All right. Well, what we're going to do is we're going to take this separation of variables here, and we're just going to plug it into our Laplace's equation where we don't have to worry about that last term. All right. So, the other thing we can do right away is we could see that every single term, even the one we killed, has a 1 over r squared out front. So we could just multiply everything by r squared, and then on the right-hand side, we have a 0. So we basically can just eliminate all of these r squared factors. All right, so then we have, let's see, d by dr of r squared, d by dr of r times theta, plus 1 over sine theta, d by d theta, sine theta, d by d theta of r theta. Okay, and so that has to be equal to 0. You can probably see what's going to happen. All of the r dependence is in this capital R, so this theta comes outside. All of the theta dependence is in capital theta, so this r comes outside. So let me take those out and let me divide by r times theta all at once. And so we're going to get 1 over r, and now the partial derivatives are just going to become ordinary derivatives because they're acting only on functions of r. So d by dr r squared d by dr acting on r plus 1 over sine theta times capital theta d by d theta sine of theta d theta d theta. I hope that's right. That all has to be equal to 0. Let me check. Yeah, I think that looks probably okay. All right. And then you know what we're going to do is we're going to set these two equal to the same constant. We're just going to change the sign in front of one of them. Okay, so let's go ahead and do that. So we will set each term equal to a constant, but with opposite sign. It probably is not going to surprise you, but I'm going to use a weird form for the constant we're going to choose. And you'll see why very quickly why we chose this form. So it will be convenient to set our constant to be L times L plus 1. Okay. The reason that that's going to be convenient is because we're going to end up taking derivatives of something like r to the L. And when we take two derivatives, we get these like L's coming down. We'll see it in just a second. All right. So our two equations are. So we have d by dr, r squared dr dr. That one I'm going to set equal to plus L times L plus 1. And then there's a 1 over r up front. I'm just going to multiply that over here, and we'll stick our r here. So this is our first differential equation that we have to deal with. And then the second one is, what is it? 1 over sine theta, d by d theta. I think it's sine theta, d theta, d theta. That one we're going to set equal to minus L times L plus 1. And then I'm going to multiply by that theta that we had there in the denominator. And we'll say that's equation 2. All right. So let's start with equation 1. The general solutions to 1 are. I'll write down the answer and then we'll confirm that that's the case. R of r is equal to a r to the L plus b r to the L plus 1. Okay, so let's check it out. So what do we need? We're going to need a dr. Okay, so if I take the derivative of this, I'm going to get a factor of L. So we'll get L a r to the L minus 1. And then I think we'll get a minus L plus 1 times b over r. And then it should just be L plus 2, right? So we have to lower the power by 1. So lowering our power in the denominator is increasing it by 1, increasing it by -1. Okay, good. Well, the other thing we have to do is before taking the second derivative, we have to multiply by r squared. All right, I can do that. R squared dr dr is equal to L a r. Our L plus 1 becomes L, or L minus 1 becomes L plus 1 because we added 2 powers of r. You can now see that when I take the next derivative, I'm going to get L times an L plus 1. That's why we chose our constant in that way. Okay. And then we have minus L plus 1 B. I have to multiply by R squared. That gets rid of the plus 2. So we get RL. You can see now when I take the derivative a second time, I'm going to get this factor of L over here. So we have L times L plus 1 again. Okay, so then finally, d by dr, r squared, dr, dr. So we have to take the derivative of that line. And it's equal to L times L plus 1 times AR to the L. It will be a plus because we'll pick up another negative sign from the derivative. B over R to the L plus 1. And I think that should just be our original R to R. And so that works. It's clearly the solution. All right. What about equation 2? That's the one that's a little more challenging. So next, we consider 2. I should just write it down again because it's far away. D by d theta of sine theta, d theta is equal to minus L plus 1 sine theta. All right. Before we do this, let me go back. I want to go back to the notes that we took a week ago. I don't know if I can find them. We'll try to find them. Whoops. So, because I want to just remind ourselves of something. Let's see if I could spot them here. Maybe it's here. So this is all the stuff we wrote down last time. Here it is. Equation number sign. Our very first introduction to Lengendre polynomials were that they were a solution to this differential equation. And when you look at that, it looks nothing like the theta equation that we just wrote down. But I'm going to try to show you that they, in fact, are related. Oh, sorry, I got the wrong thing. Here we go. Okay, so let's just make a couple comments about this. So let's just recall that the Lengendre polynomials PL of X were solutions to number sign. My goal is to show that 2 and number sign are related. And so it's going to be the Lengendre polynomials that are going to be the solutions for this theta function. All right, so how are we going to do that? What we're going to do is we're going to make a change of variables. Okay, so I'll just renumber this as 2 again. So let's consider a change of variables in 2. All right, what change are we going to make? We're going to say X is equal to cos theta. This capital theta is a function of theta. If I write X is equal to cos theta, I can re-express capital theta in terms of this variable X. The thing we have to be careful about now is that our differential equation has derivatives with respect to theta. So we're going to have to use chain rule, convert those to derivatives with respect to X. And let's see if we can do that. There's one other useful thing that will happen here is let's just make a mental note for later that sine theta squared, I can of course write as 1 minus cos squared theta. But cos theta is x, so I could also write this as 1 minus x squared. And just looking at number sign, that 1 minus x squared that we see up there, that's going to end up being a sine squared theta. Okay, so let's see how this works. If I make a change of variables like that, derivatives with respect to theta become, by the chain rule, derivatives with respect to x with a correction factor here, dx d theta. But if x is cos theta, then dx d theta is minus sine theta d by dx. Okay, so with all that in available, what we're going to do is we're going to work on this thing. So let's get a copy of that. Oh, paste it. What are you doing? Oh, you son of a bitch. Okay. Did I not hit copy? Pretty sure I did. Okay, here we go. All right. Well, the first thing we'll do is we'll rewrite this d theta here as minus sine theta d by dx. Okay, so we have this is going to be equal to minus sine theta d by dx of sine theta, and here I'm just going to use chain rule to write this as, I mean, it's the same thing, right? It's just the minus sine theta d theta dx. So basically, I've just used this relationship twice for the two derivatives that we have. All right. Fair enough. Then what could we do? We're going to have a sine theta. I have two negative signs which cancel, and I have a sine squared in here. So I'm going to have a d by dx of sine squared theta d theta dx. And so now we've got to be a little bit careful. Because if we're not careful, we might just say, oh, this derivative just acts on the function of x here, doesn't act on theta. But remember, theta and x are related to each other. And in fact, we already said sine squared theta is 1 minus x squared. So this thing is 1 minus x squared. And so what we're left with is d by dx of 1 minus x squared d theta dx. And now we're ready to go. Okay, so now we have two functions of x. We have to use product rule. So we take the derivative of the first term of the product is minus 2x. And it multiplies d theta dx. And then we have to do plus. We write down the first factor. And then we take the derivative of the second factor. Like so. All right, good. So we're ready then to plug this back into equation 2. Where did it go? There it is. So we just worked on all of this, and we just have to say that's equal to L times L plus 1 sine theta times theta. So therefore, 2 becomes, I guess I'll write it down, but if you noticed, we have a sine theta here, and then we also had a sine theta on the right, so they're going to cancel. I'll write it as 1 minus x squared d squared theta dx squared minus 2x d theta dx is equal to, what was it? It was minus L times L plus 1 sine theta times theta. Hopefully I remembered that right. We'll find out in a second. Cancel the sine thetas. Now, what I'm hoping is that this thing is just number sign. Where is number sign? There it is. 1 minus x squared, 2 derivatives, minus 2x, 1 derivative, minus L times L plus 1 times the function. So this is 2 derivatives with the 1 minus x squared minus 2x, 1 derivative is minus L times L plus 1 times the function. This is exactly the form of number sign with x is equal to cos theta. So therefore, the solutions are the Lengendre polynomials. And that's why we spent so much time kind of developing this idea and learning about some of the properties of these polynomials and the fact that they're orthogonal and the fact that we can expand functions in terms of the Lengendre polynomials. So therefore, that means theta is equal to PL of x, but x we said was cos theta. And we should put a little subscript L on our theta solutions because L is equal to 0, 1, 2, up to infinity. All right. Okay. So now we have the solutions for our capital theta, and we have the solutions for, where did it go? For capital R. So we should put those in a box maybe. And we know that our potential is going to be the product of those two. And in fact, if for any value of L, we can add different products together and we can make the superposition. And so the general solution for the potential. So the general solution for V of R theta, when we have azimuthal symmetry, is V R theta is equal to at L equals 0 to infinity of our R solution look like this. R to the L plus 1, I think. Yeah. And then our theta is given by the Lengendre polynomials. And notice we haven't specified anything other than the fact that we have azimuthal symmetry. So this applies to any problem in separation of variables for Laplace's equation when you have something that's a potential that's going to be independent of phi. All right. So let's see an example of how we can use this. So, example. Let's find the potential inside a hollow sphere of radius capital R when the surface of the sphere is at potential. So we'll just say V naught, and it has some theta dependence. We'll ultimately have to specify that theta dependence, but for now, let's just try to see what we can do. Just like we did in Cartesian coordinates, the whole game now is to find the values of the unknown coefficients. So for example, AL and BL and well, actually those are the ones we have to deal with. All right, so we need to come up with boundary conditions. Match the boundary conditions. What do you suppose the boundary conditions are? Yeah, we're given the one, and so one of them is that at a point on the surface, it would have to be equal to this V naught of theta, right? There's one more that's going to be important, and it's maybe one that's not so trivial to think about. What would you expect to happen at the center of the sphere? Zero. Yeah, maybe it's not zero, but we want to avoid what? We want to avoid the divergence, right? If we had like a spherical shell with some charge on it, you know, as long as I had a finite amount of charge, I wouldn't expect the potential at the center to be infinite, right? It'd be some finite number. And so I want at r equals 0, I want this to be finite. And that will turn out to be important. Okay. So this is the r equals 0 boundary condition, and this is the r equals capital R boundary condition. Okay, so well, let's look. What does this first boundary condition tell us about either the A or the B coefficients? Which one has to be 0?
A. B.
AL has to be 0. Well, what we're trying to avoid is the potential diverging when we set R equal to 0.
B.
Yeah, so here we're dividing by R to the L plus 1. So if I put in R equals 0 there, then that whole term explodes. And so that's not good. And so we don't want that. So from boundary condition 1, BL equals 0 for all L, otherwise the potential at R equals 0 diverges. Okay, that's good because that helps us simplify our solutions quite a bit. Because if we're going to just say that all BLs are 0, then I get a nicer looking potential. All right. So next we have to think about boundary condition 2. So from 2, what do we require? On the surface of the sphere, we're going to end up with, let's see, we have an AL, and the only thing that changes is on the surface, our radius is equal to capital R. So, okay, so we have a capital R here. PL cos theta, and we need that to be equal to V0 of theta. All right. You know, it's kind of I find this kind of like a humorous sort of kind of a twisted joke, because we've done all this work, we've come up with some expression for our potential, and what we ended up with is an infinite sum of Legendre polynomials. But I can write any function in terms of Legendre polynomials. So that means my solution is any function I could imagine on this interval -1 to +1. So it's kind of this kind of twisted joke in that we've done all this work and we still have no information about our solution. But at the same time, we have a prescription for finding these coefficients when we have a series expansion like that. We're going to use the inner product. Okay, so to go further, we need to select the AL coefficients to match the theta dependence of V0 of theta. Okay, are we doing 15 minutes? All right. Okay. So what do we know? We already know that the integral from -1 to 1 of PL of x, PL prime of x dx is equal to 2 over 2L plus 1 delta L prime. This was the normalization factor that we wrote down, I don't know, 20 minutes ago or something. Okay, so what we're going to do is we're going to try to do this kind of calculation so that we can find out our AL coefficients. So let's examine. So let's see. We have to be careful. Let me back up for a second. We know that x is equal to cos theta. That's what we required for our theta differential equation. So when x is equal to -1, what's the corresponding value of theta? Pi, that's right. When x is equal to +1, the corresponding value of theta is 0. So what we're going to have then is we're going to look at an integral from, let's say, pi to 0. So if this would correspond to x equals -1, this to x equals +1. And then we're going to take our potential on the surface of the sphere, and I'm going to multiply it by PL prime of cos theta. And instead of integrating with respect to x, it's going to be d cos theta. Okay. All right. So what happens when we do that? The d cos theta is minus sine theta d theta. I can use the minus sign to invert the limits of the integration, which I like better. I like having my lower limit be a smaller number, so I'll do that. And so PL prime cos theta sine theta d theta. All right, so this is what we're going to try to work on, and we're going to substitute this expression in for v of capital R theta. So it's 0 to pi, and then we have the sum from L equals 0 to infinity of AL. That's what we're trying to find. I think it's capital RL. And then we had a PL cos theta, PL prime cos theta, sine theta, d theta. All right, good. You can see we're going to end up with an inner product of Lengendre polynomials, and we know what that answer is. All of this stuff, none of this stuff has any theta dependence, so we're going to take that out of the integral. And so this is equal to the sum of L equals 0 to infinity, AL, RL, the integral from 0 to pi of PL cos theta, PL prime cos theta, sine theta, d theta. And this is equivalent to -1 to 1 of PL of x, PL prime of x dx. And we know that that's equal to delta L prime. It's 2 over 2L plus 1. Okay. The Kronecker delta is like, it's like the delta function for sums. And it's a beautiful thing because it's a killer of sums. Just like the delta function kills integrals, the Kronecker delta removes sums for us. 2 over 2L plus 1. Okay, so what are we going to get? Well, you tell me, what is this delta function gonna do? We're summing over L, what's the only non-zero term we're gonna get? The L prime one, right? So we're gonna get 0 plus 0 plus 0 plus 0 until we hit L prime. When we hit L prime, this product of delta will be a 1. And so we'll get an AL prime. And then it's RL, R to the power L prime, and it's 2 over 2 L prime plus 1. Okay, so if we go back here, what we can do is now we can isolate for AL, and we can say this AL is all of this stuff multiplied by the original integral way up at the top there with the potential in it. Okay, so solving for AL. Okay, what's it gonna look like? I'm gonna drop the primes because I don't need to have primes now because I've gotten rid of the other L. So I'm just gonna call it AL. So AL is going to be equal to 2L plus 1 over 2. And then we have also an R to the L. So I'll take the R to the L there. And then it's multiplied by this integral 0 to pi V at the surface of the sphere, depends on theta, PL cos theta sine theta d theta. And so there's our coefficients. The only way that we could go further is somebody has to tell us what this function is. Okay, but this is a general solution for any Laplace type problem in spherical coordinates with azimuthal symmetry. Okay, so let's see. Okay. Suppose, so to go further, we need to specify V of our theta is equal to this V naught of theta, for example. Okay, so let's suppose V of theta, V naught of theta is equal to K sine squared theta by 2. Where K is some constant. All right. Does anyone know what's a trig identity for sine squared? Yeah, so you're right. What I remember is sine squared theta is 1/2 of 1 minus cos 2 theta. So if we then say theta is theta by 2, then that's going to be 1/2 of 1 minus cos theta. Okay, so that means that our potential is equal to K over 2, 1 minus cos theta. All right, let's think about this a little bit. Let's go PL of x and PL of cos theta. When L equals 0, PL of x was 1, so PL of cos theta is also 1. When L equals 1, what was P1? What was the second Lengendre polynomial? X. And so if we say x is equal to cos theta, we would just get a cos theta here. And in fact, I don't need to go any further because I can write this potential as a sum of Lengendre polynomials, right? So notice that K over 2 1 minus cos theta. Well, this 1 is just P0. And this cos theta is just P1 of cos theta. So I could equivalently write my potential as V0 of theta is K by 2 P0, I think it's a minus, yeah, minus P1. Okay, well, all we're gonna do is we're gonna put that into our AL coefficient finder. So therefore, AL, it was a long expression, right? There's like a 2L plus 1 divide by 2R to the L, integral from 0 to pi, and then it was our potential. So our potential is K2, K over 2, P0 minus P1, and then it was PL sine theta d theta. Okay, I really don't care about the K over 2, so we could say this would be like K over 2, 2L plus 1 over 2 R to the L. And then we're going to have the integral from 0 to pi of P0 PL sine theta d theta minus the integral from 0 to pi of P1 PL sine theta theta. All right. So if I put in L equals 0, what are we going to get for this integral? Is it going to be, let me ask this question, is this going to be 0 or non-zero? If L is 0. And non-zero, that's right. If L is 0, what's this one going to be? 0. These are the inner products, right? Okay, then let's go L equals 1. What's this integral going to be? This one? Non-zero. Okay, non-zero. And then I could take any other value, L equals 2, 3, 4, 5, 6. They're all going to be vanished because we have orthogonal functions. So because the PLs are orthogonal, only the L equals 0 and 1 cases give non-zero results for AL. And in fact, we could write them down. Do we have time to write them down? Not really, but we will write them down anyways. Okay. So for L equals 0, we're going to get A0 is equal to K over 2. L is 0, so we get 1 over 2, I think. 1 over 2. And then we have this integral, and then I forget what the result of this inner product is. What was it? It was 2 over 2L plus 1. So it's 2 over 2L, but L is 0 plus 1. And so I think it's just K over 2. I hope that's right. It is. It is positive. This one is positive, right? We're going to get a negative sign for the other one. And so A1 is going to be equal to what? K over 2. We're going to have L equals 1. So it's 2 times 1 plus 1 is 3. And then we're going to have a divide by 2R. Okay. And then we're going to pick up a minus sign from the second integral. And then we're going to get 2 over 2 times 1 plus 1. Hopefully this works out. And so what's that going to do? Our 3's are going to cancel. Our 2's are going to cancel. If I get this right, I get minus K over 2R. Oh, good. Okay. Good. And so those are our two coefficients. Those are the only non-zero ones. And we can go all the way back here and say, no, it's all the way back here and say, I know all of the BLs are zero. And I know that there's only two ALs that are non-zero. It's A0 and it's A1, and we found them both. And so we have the complete solution for this potential. What I'll do is I'll summarize all of this next time, and then we'll move on to a new topic. All right, thanks very much. I'll also have the midterms for you Monday. All right, thanks everyone. Yeah. Sorry, I didn't understand the question.
That I have my notes for the lab.
Oh, yeah, it's in the lab now. So you